Hello, so today I will be going over shifting operations. So this will include shifting left and shifting right. I will also be talking about arithmetic shifts. So let's start with the shift left. So we call this shift left, and you can have shift left logical or shift left arithmetic. But for now, let's just do a logical shift. So let's take the number 0010, for example, and all we're going to do is we're going to shift our bits one bit to the left. So this bit goes here and it goes away. This bit goes to this place, this bit goes to this place, and this bit goes to this place. So simply we rewrite as 0, 1, 0, 0. So we just shift in a 0. So let's observe what's going on here. So this number in binary is 2. And this number in binary is 4. The relationship between these is 2 times 2 is 4. But just so you can see that this is not just a coincidence because it's an even number or whatever, we're going to use, let's do the number 3. So this is 3. And when we shift over, we get 0, 1, 1, 0, which is equal to 6. So this will apply for every single number unless you are shifting away your bits, your only bits. So let's do an example of that. So let's do an example where you have 1, 1, 0, 1. If we shift these, we get 1, 0, 1, 0, and this number is equal to 8 plus 4 plus 1 is 13, and this number is equal to 10. So shift left logical only works when you're not shifting away your bits. So now let's do a problem with shift right. So when we shift right, let's take the number 0, 0, 1, 0, and we just perform the same operation, but we're shifting the other way this time. So this number equals 2, and we're just going to shift all our bits to the right. So we get 0, 0, 0, 1. We shift in a 0. So this is equal to 1. Let's do another example. 0, 0, 1, 1. We shift it to the right once, and we get 0, 0, 0, 1. Well, what's going on here? This is 3 divided by 2 is not 1. So let's just do another example so you can see what's going on. So let's take another odd number. For example, let's do the number 7. And let's shift to the right once. So here we have the number 7 and we have the number 3. So in other classes, you may have learned about integer division. So when we do 3 divided by 2, but with integer division, we get 1. And when we do 7 divided by 2, in integer division, we get 3. Basically, if you don't know what integer division is, this number would be 1.5, and this number would be 3.5. But in integer division, we forget about this. We truncate our number, and we are just left with integers. So that's what's going on here when we shift right. So now let's go over an arithmetic shift. So let's say we have the number 0, 0, 1, 1, and we want to shift left, and we want to have an arithmetic shift. So when we shift left with an arithmetic shift, we're going to shift in a 1 instead. So let's do that. So that's our shift left arithmetic. And let's say we wanted to shift right. Let's say we have and we're going to shift in a 1 on the right side. So we shift in a 1, and then we get 0, 0, 1. So let's go over some problems that you may see in class or on an exam, or maybe you just need to do an operation where it'll require multiple shifts. So you'll see something, maybe you'll see something like 3 and then 2 less than signs and a 2. So what this is telling you to do is you take the number 3 and you shift left twice. So let's do that. And we shift left twice, and we're left with 1, 1, 0, 0. So let's observe what's going on here. So this is the number 3, and this is the number 12. So when we do a shift to the left, we're basically multiplying by a power of 2 every single time we shift. So when we do 3 times 2 for one shift, we get 6. And then when we do 2 shifts, we multiply by 2 again, and we get 12. So that's what's going on here. Let's do another practice problem. So let's do something like 4. Shift left, 2. So we have the number 4. And we want to shift left twice. But when we shift left twice, we're left with 0. All zeros. The reason for this is a term that you may have heard of before called overflow. So if we were to do 4 times 2 for one shift and then times 2 for another shift, we would get 16. And 16 is greater than our range of bits for a 4-bit number. But let's say we had a 5-bit number. Then we would be able to shift this number twice, and we would get this, which is equal to 16. So let's do some right shift problems. Let's take the number 12, like we had before, and so we have 12, and we're going to do greater than signs to show we're shifting, and we're going to shift it twice. So let's take the number 12, and let's shift it to the right twice. So we get 0, 0, 1, 1, and this is equal to 3. So we're basically doing integer division twice. So maybe let's do an odd number so it's easier to see here. Let's try 1. So 1, 0, 0, 1, and so that number is equal to 9. And we're going to shift that right twice. So let's shift this number to the right twice. We drop this 1, we get rid of it, the 1 on the right, and then we get 0, 0, 1, 0. So what this is doing is we do integer division, and so 9 divided by 2 is an integer division is equal to 4, and then we divide by 2 again, and then we get 2. So that's what's going on here. So this number 0, 0, 1, 0 is equal to 2, which is what we expect. So that will be what you'll see if it asks you to do an arithmetic shift. All you have to do is shift in a 1 instead.